Hello and welcome to the development of simplified factors for lateral distribution of loads of non-standard gauge NSG axles webinar. My name is Paula Hyman from the Ohio LTAP Center, and I'll be your technical support for today's webinar. Just a couple of items to cover. If you have questions throughout the presentation, please put them into the questions pod and our presenter will address them at the end of the presentation. There is one item available to download in the handout section. If for some reason you're unable to download the handout, put your email in the questions pod and I will send it to you directly. All documents will be emailed after the completion of the webinar to the group. This webinar is being recorded. Providing that the recording is successful, the YouTube link will be emailed to all participants and uploaded to our LTAP website. I want to thank you in advance for your participation with that, and I'll pass things off to Mr. Travis Butts, Senior Bridge Engineer with Burgess & Nyepel.
All right, thanks, Paula. Oya and I are going to turn our cameras on here briefly just to introduce ourselves, but I'm Travis Butts. I'm a Senior Bridge Engineer with Burgess & Nyepel, and I was the principal investigator for this project.
And I'm Oya Watt. My experience in bridge design is 5 years. I've been assisting Travis with this project.
All right, so as Paula said, this is the development of simplified factors for lateral distribution of loads of non-standard gauge axles. So hopefully you joined to hear about non-standard gauge axles, otherwise you're in for a rough 45 minutes or so. But yeah, it'll be Oya and I presenting. And I'm trying to, there we go. So this first slide is the research team that worked on this project. So from Burgess & Nyepel, it was Oya and myself and Roger Kochman, another senior engineer with BNN. From ODOT Research, Vicki Fowd and Jennifer Spriggs supported us on this project. And the technical advisory committee from ODOT consisted of Amjad Waheed, Alex Young, and Brad Knoll from the Office of Structural Engineering, Josh Thiemann from Permits, and Mike Moreland from Maintenance. So they provided the guidance or the vision for what this project is, and also supported us throughout to help us achieve the ultimate conclusions that we did. So the reason for this project is start off with an explanation of the Ohio Hauling Permit System, or OHPS. That's the automated system that ODOT uses to evaluate permit loads, so vehicles over the normal legal limit. And they evaluate over 335,000 of those loads every year, so a lot of them. So by necessity, this is an automated system that runs these vehicles over many bridges to evaluate whether the bridges are capable of safely carrying the load. A lot of those permits are non-standard gauge axles, which means an axle where the gauge width is not 6 feet. So 6 feet is a standard vehicle, either less or more is a non-standard gauge vehicle. Those vehicle types are currently evaluated by applying modifiers to standard gauge distribution factors. So the AASHTO distribution factors are based on standard gauge vehicles. And where the vehicle is non-standard, that there's a set table of distribution factors that are applied to those values before it's run through the automated OHPS process. And the way the process works is that it will indicate which bridges do not pass the evaluation, and those bridges come back to Office of Structural Engineering, where they have to evaluate individually those bridges to see if the vehicle works. So that's a very time-consuming process. The reason for this project is the modifiers that are currently being used for non-standard gauge vehicles are based largely on historical precedent and not on an established research project. So this is that project to take a look at those modifiers and adjust them as appropriate. So the goal of the project is to produce an accurate and simplified method that will improve the process of analyzing non-standard gauge vehicles. And that ultimately would take the form of a table or a matrix of correction factors that could be applied to distribution factors, either standard spec load factor design distribution factors or LRFD distribution factors, both of which get used in ODOT ratings, and incorporate those factors into the OHPS. The project's going to look at gauge widths that range from 3.5 feet out to 24 feet and includes 4 structure types, which are the most common structure types in Ohio or on the ODOT system, which are reinforced concrete slab bridges, prestressed concrete side-by-side box beam bridges, prestressed I-beam bridges, and steel multi-beam bridges with a concrete deck. So the first few slides will give you some background of what we looked at as far as guidance already published and past research before we went into the study that we ultimately performed. So this first slide is about AASHTO in particular, and starts off with just an explanation of what a distribution factor is. So a distribution factor is the fraction of the bridge live load that's assigned to a specific portion of the bridge. In this case, we're talking about an individual beam or a portion of a slab superstructure. So having a distribution factor simplifies analysis in that you don't have to do a 3-dimensional analysis of each bridge to determine how much load goes to each component. You can assign based on the properties of the bridge a portion of the live load to a component. There are equations for distribution factors both in the AASHTO standard specifications and the AASHTO LRFD specifications. Those are 2 different sets of equations that give you 2 different sets of numbers, but both get applied to Ohio bridges. The distribution factor equations are derived for standard gauge axles. So the AASHTO design specifications don't address non-standard gauge axles at all. It does come up in the AASHTO manual for bridge evaluation, which deals with load rating and permit loads. And it includes some commentary on non-standard gauge loading. The bottom paragraph is that commentary with some excerpts from it. So it says AASHTO LRFD distribution factors were developed using a standard 6-foot gauge width. Sensitivity studies indicate that most parameters such as gross weight, number of axles, and axle spacing have only a small effect on the load distribution factor for flexure. It was found that the single most important parameter is gauge width. The distribution factor is generally lower for increased gauge width. So that restates some of the things we already knew, and also says, in general, as the vehicle gets wider, the distribution factor gets lower, as you would expect. But it doesn't give any guidance as far as what magnitude of reduction to take. So that's what we're trying to determine. So moving on to some past research, what you see here is NCHRP Synthesis 359, which is Bridge Rating Practices and Policies for Overweight Vehicles, and this is from 2006. And this document collected information from US states and Canadian provinces about permit policies. And it also dealt with non-standard gauge vehicles, and it made the statement that no national specification for lateral distribution exists. And it also noted there was considerable disparity between how individual states handled these load types. And it gives in the appendix a table of all the states and all the states that responded and how they address non-standard gauge vehicles. And as they state, that there's considerable disparity. There's lots of different methods to deal with these. There's a few past projects that did similar studies to what we did. This one is moment and shear load distribution factors for multi-girder bridges subjected to overloads. That's from 2012. It looked at multi-girder bridges specifically, and it considered factors like span length, girder spacing, girder stiffness, gauge width, skew, and the number of spans. And it looked at 118 different multi-girder bridges, 16 different load cases, and they ran those analyses. They used the data to derive statistically based distribution factor equations, which you see below. And you can see the plot of that against their finite element results, and then also standard distribution factor equations from AASHTO. So this gave us some valuable data about the relevance of these different parameters, but it didn't give us a simplified correction factor. You see those equations are complex and can't easily be summarized into a table of corrections that's applicable to everything. So we were able to use some data from there, but not use this specifically for our study. This is another study done in Iowa for the Iowa Department of Transportation in 2016. This looked at non-standard gauge loads on prestressed concrete, steel, and slab bridges, used randomly selected bridges from the Iowa database. And it had 22 different types of single axle and four-wheel line loads. And they used these results to establish maximum allowable loads for different non-standard configurations. So again, lots of valuable data as far as what they looked at and what affected the distribution, but not directly consistent with the goals of what we're trying to achieve. And a third study, this one from 2019, load distribution in short bridges subjected to oversized vehicles. This looked at 9 composite steel girder bridges and looked at 2 and 4-wheel line vehicles with the widths ranging from 6 to 12 feet. And this derived distribution factor equations in a similar format to what AASHTO LRFD uses. So you can see those below for moment and shear. And again, this gives us a complex relationship as far as how gauge width affects distribution and looks specifically at a single bridge type. So what we did with those studies is we made this table to summarize what we had collected. As I said, they're not fully compatible with what we're going to do, but they do have a lot of useful information as far as how these parameters affect distribution. So we tabulated all the parameters we considered including in our study, and then the 3 past studies, we noted whether these factors were found to be significant, non-significant, or whether they were not included in the study. We also noted whether these different factors are already included in the calculation of standard distribution factors for both standard specifications and LRFD. And then also, can this factor be considered when we're inputting into the OHPS system, which we'll talk about this in a bit more on the following slides, but the OHPS input is limited to the vehicle specific information. So you enter correction factors for the vehicle, but those factors are applied to all of the bridges in the system. So bridge specific information can't play into our correction factors. And then based on that data, we noted them in the right, whether the factor is included and why we did or did not include it. So this is also color coded. The green ones are the ones we included. The light orange is what we did not include. So span length was found to be significant in all the studies. It is included in the LRFD factors, but not the standard specs. It can't be considered for input, but it's still a significant factor in the study. So we did, that is one of the parameters we varied in our study. Deck thickness, it is a significant factor, but on ODOT structures, it's a set number. It has been for a long period of time. That the deck thickness is determined by the beam spacing on multi-beam structures, and it's a set number for each of the structure types we looked at based on span. So we did not include that in the study. We're just using the ODOT standard for the thickness. Girder spacing, girder stiffness, both significant factors. That was concluded in all the studies. They do play in sometimes to the distribution factor calculation. They're bridge specific. They can't be included in OHPS, but they are significant factors we included in the study. One of the studies looked specifically at end diaphragms and how they affect the distribution. That's not normally considered in AASHTO. It's kind of beyond the scope of what we're going to look at. We did not include that factor in our study. Gauge width is the focus of what we're doing. So yes, that's significant, and yes, that's included. Skew, again, one of the studies looked at it, and it definitely affects things. It's already considered in the LRFD factors, and it's normally not considered at all in standard specs, so we elected to exclude that. Number of spans, it was determined to not be included, not be significant in the studies, but we're looking at continuity in some of our structure types, in the multi-beam and the slab specifically, and we did feel like it would be significant there, so we did elect to include at least continuity in our studies. And the number of wheel lines, again, that's a vehicle specific data point that we definitely did want to include, and it's definitely a significant factor. So a little more about ODOT's OHPS process and how they currently handle non-standard gauge vehicles. So we talked earlier about how they use a set table of correction factors. That this is that table on the right side of the slide. So it's based on gauge length and number of tires, which it's important to note, number of tires is actual number of tires, not number of wheel lines. So 4 tires can mean two sets of dual tires, and 8 can mean 4 sets of dual tires, not necessarily single load points. The data that came from Kansas DOT references a paper called Effective Width Method for Determining the Lateral Distribution of Wheel Loads for Non-AASHTO Axles. This came from McClellan Engineering in Dallas. It's undated, it's written on a typewriter, so it's fairly old. We took a hard look at that paper in relation to this table, and we were not able to duplicate the numbers in the table. So we're not sure what the basis for these factors are. So again, that's the reasoning behind this project, is we want to try to validate what these correction factors are. The OHPS uses software called ProMiles, and this is a shot of the input for a vehicle into ProMiles. So this is the actual screen that the ODOT engineer uses. So it's got the entity requesting the permit inputs the axle spacing, the weight of the different axles, the number of tires, the details of the tires as far as the width and the size of the tire and the gauge of the axle. And then the reduction factor over on the right is input by the Office of Structural Engineering based on the data that is input. So they're pulling that 0.631 off the table on the previous sheet based on the 18-foot gauge and the number of tires entered. So this gets entered into the system. ProMiles then automates a run of all the bridges in the path of the vehicle in BRR, AASHTO BRR software, and then reports back which bridges either don't work or bridges that it's not capable of evaluating in BRR, which those are the bridges that then come back to OSE to evaluate independently or individually. So moving on to the study we did to calculate those factors. We designed the study based on bridge information from ODOT and vehicle information we received from ODOT. So it's a series of finite element analyses that isolate the various parameters that we identified from the previous studies to try to calculate those factors. The vehicles were based on a set of vehicles that were provided to us, and we used a wide range of axle of wheel line spacings and a number of wheel lines, so up 2 to 8 wheel lines in the study. We went from the ODOT standard drawings to determine the specific bridge characteristics, and also looked at a number of typical bridge plan sets and came up with the configuration of the various bridges that we looked at. So the study consisted of 168 bridges of those 4 bridge types, 34 different axle configurations, and we used Midas Civil software to perform the modeling. So with that, I'm going to pass it over to Olya to give the details of the study and the analysis methods we used.
Thank you, Travis. As Sharon mentioned, I'm going to talk a little bit more about the parametric study itself, as well as about MIDAS modeling techniques. I'm sorry about the delay. I was trying to switch the slide. My apologies, but it works now. Travis already mentioned that the parametric study included 4 bridge types. The bridge types were side-by-side prestressed concrete box beam, concrete slab, prestressed concrete I-beam, and steel multi-beam. Side-by-side prestressed concrete box beam is a typical lower-cost prestressed concrete bridge that is used for short to medium span arrangements. Prestressed concrete box beam bridge consists of rectangular box beams that are connected together with steel tie rods and cast-in-place shear keys. The wearing surface for this kind of bridge can be asphalt or concrete. If concrete is used for the wearing surface, then it is connected to the beams by shear stirrups. And in this case, the bridge is considered to be composite. Concrete slab bridge is a typical cast-in-place reinforced concrete superstructure, which is typically used for short spans. It can be a simple span or a continuous span arrangement. Prestressed concrete I-beams and steel multi-beam bridges are typical in many states. These kinds of bridges consist of multiple beams that are connected together with cross frames or diaphragms. Typically, these kind of bridges have composite reinforced concrete decks. In Ohio, steel multi-beam bridges in multi-span arrangements are generally designed to be continuous. As far as prestressed concrete I-beams, in the past, Ohio allowed to design prestressed concrete I-beam bridges in multi-span arrangements as a simple span for dead load and as a continuous span for live load. The continuity was achieved by means of continuity diaphragms at piers and by providing continuous longitudinal steel in concrete decks. However, currently, prestressed concrete I-beam bridges in multi-span arrangements are designed discontinuous. Because due to previous practice, we currently have a lot of existing bridges on a highway system that were designed as continuous for live load. We included both simple span and continuous span arrangements for prestressed concrete I-beam bridges. Do you mind switching the slide? Oh, okay, there you go, it works. For the bridge types to be included in this study, we looked at ODOT standard drawings. We also looked at other industry standards, such as, for example, NSG standard drawings for steel bridges. And we reviewed ODOT, typical ODOT inventory. We looked at different number of spans depending on the bridge type. The number of spans varies from 1 to 3. We looked at different number of bridges per bridge type, as well as different span ranges for different bridge types. As far as the beam spacing goes, box beams typically come in 3 feet or 4 feet width. For the purposes of this parametric study, we chose 4-foot wide box beam, and we held our spacing constant. For concrete I-beam and steel multi-beam bridges, we varied beam spacing. We included spacings of 7 feet, 9.5 feet, and 12 feet. For the bridge width, we used a minimum width of 32 feet, which included two 12-feet lanes and two 4-feet shoulders. If necessary, for concrete I-beams and steel multi-beams, we increased bridge width to accommodate at least 4 beam lines and 2 3-feet overhangs. For the vehicles to be included in the study, we requested the data from Ohio Department of Transportation. They provided us with a list and description of typical non-standard gauge axle permit loads that they typically observe on Ohio highway system. After analyzing the information on the vehicles that we received, the range of axle gauges was determined to vary from 3.5 to 24 feet. For this parametric study, we did not look at longitudinal arrangement of axles. We only looked at single axle lines, and that is because in Ohio OHPS system, correction factors are applied to individual axles versus the entire vehicle. For this study, we looked at axles with 2, 4, 6, and 8 wheel lines. For the vehicle weight, we kept it constant. Because our analysis was linear elastic, and because the correction factors were developed based on proportion, vehicle weight would have no effect on the result of this study. In total, we looked at 34 different axle configurations. For the purposes of this study, axle was defined as a line of transverse loads on a vehicle. Axle consists of multiple wheel lines. Wheel lines is a single load point on an axle. One wheel line can consist of a single tire or a set of dual tires. Depending on the number of wheel lines, we split our axle configurations into 4 categories, 4 types. Type 1 includes axles with 2 wheel lines. Type 2, 4 wheel lines. Type 3, 6 wheel lines. And type 4, 8 wheel lines. Axle configuration number 2 is a standard 6-foot wide gauge configuration. The correction factors for the remaining 33 non-standard gauge axle configurations were derived relative to axle configuration number 2. Now I will briefly talk about MIDAS modeling approaches. For concrete slab bridge, modeling methods are well established. For our MIDAS models, we modeled concrete slab using 2-dimensional shell elements, which are capable of modeling biaxial bending effects. We refined our models following the guidelines from FHWA, and we kept decreasing the mesh size until our results converged. We ended up using mesh size of 1 to 2 feet for all of our concrete structures. For steel multi-beam and prestressed I-beam, we follow the guidelines from the Manual for Refined Analysis. We modeled our beam as beam elements. And we modeled the deck as two-dimensional shell elements. We used plate and eccentric beam type models. We ended up using a minimum of 10 elements per span, a minimum of 2 deck elements between beam lines, and we did not exceed an aspect ratio of 2:1. Prestressed side-by-side box beams are designated in AASHTO RFD specifications as types F and G. AASHTO specifications provide equations to calculate distribution factors for these bridge types. The equation for composite and non-composite box beam distribution factors is the same, and it comes from NCHIP report 1226/1. For AASHTO, prestressed side-by-side box beams act as a rigid monolithic unit. Therefore, in our minus model, we connected longitudinal beam elements with transverse rigid elastic links. We release links per moment to allow beams to rotate independently one from another. We calculated distribution factors for box beams per AASHTO equation, and we compared distribution factors per moment from our minus model to the AASHTO calculated values, and both were in good agreement with one another. At this time, I'm going to pass presentation back to Travis, and he will talk about the results of the parametric study and will introduce the final correction matrix.
Thanks, Olya. Okay, so the result for that analysis Olya talked about, we took and compared section forces from we ran both the standard gauge vehicle and a series of non-standard gauge vehicles. And the way we calculated the correction factor was to take the results from the standard gauge vehicle and divide them, or from the non-standard gauge vehicle and divide by the standard gauge vehicle. And we did that for section forces, which are generally moment or shear for the various bridge types. We elected to not include the actual calculated AASHTO distribution factors for a couple of reasons. One is that the standard spec versus the LRFD distribution factors are different, so there would be a different correction factor for either. And then also the way we were running the axles as single axle lines rather than as full vehicles weren't fully compatible with the way those distribution factors were calculated, especially for shear. So it didn't always make for a good comparison. But they were based strictly on, the correction factors were based strictly on analysis results. So the data we collected for the different bridge types is listed in the bottom portion of this slide. So for composite and non-composite box beams, we looked at maximum moment and maximum shear. For the concrete slabs, we looked at moment specifically, and we looked at both positive moment and negative moment for the continuous arrangements. And then for the multi-beam structures, both the concrete I-beam and the steel multi-beam, we looked at negative and positive moment and shear. So the next several slides are going to show a graph of the results for the various different bridge types. So this first one it's both prestressed I-beams and steel multi-beams. The graph shows the steel multi-beams, but the results for these two types were very similar. And what you can see, so that on the Y, the vertical axis, that is the calculated correction factor versus the gauge of the axle on the horizontal x-axis. So you can see at standard gauge would be 6 feet, so that is right here, and that corresponds to a 1.0 correction factor. And you can see we did run the one narrower gauge axle, and we got a pretty big inflation for that one, especially on the shear side. And then you can see a pretty steady reduction as the gauge increases. What's not reflected in this table is that this also reflects the various numbers of wheel lines. So there's a big drop off here at 12 feet. That's for a couple of reasons. One is that is the widest gauge two axle or two wheel line axle. So beyond that point, all of the axles have at least 4 wheel lines, so it distributes the load to more point load applications. The other factor with the multi-beam bridges is that is the widest spacing of the beams of the individual beam lines. So beyond 12 feet, the gauge is spread out to at least 3 beam lines at that point. The other factor in this tabulation is that we are not differentiating between interior and exterior beam lines, which does end up making a significant difference with the multi-beam structures, because the narrower gauge vehicles tend to have higher peaks on the exterior beam lines if you shift them all the way to the outside, because the load is distributed over a narrower area. So if we differentiated, we would get significantly different correction factors for interior and exterior. But because most of the common bridge types we're interested in have the same beams for both the interior and exterior lines, we decided early on that that's how we would make these comparisons. So this is the same plot for slab bridges, and here we were looking only at positive and negative moment. You can see those two lines follow each other very closely. And it's a similar result. We've got the 1.0 at standard gauge, and then a steady slope up to 12 feet, and then a very drastic slope above 12 feet. And with the slabs, I think that is entirely due to the distribution over more than 2 wheel lines. So once it gets spread out to 4 wheel lines, there's pretty significant reduction, because the load gets less concentrated applications, and you get lower peaks in the slab. And I saved for last the pre-stressed box beam bridges, because these were the more problematic set from our results standpoint. So these, we ran both composite and non-composite. We got very similar results for both. And you can see early on, there's a very gradual result or reduction in the correction factors. That the shear is 1.0 up to 12 feet, because we have side-by-side 4-foot wide beams. So as long as a single wheel line falls on a single beam, the shear is the same. So that's why that stays steady. And then once you get into the multiple, the 4-wheel line vehicles, you get a more drastic reduction in the shear. The moment, though, is a very gradual decline compared to the other structures. And what we found is that even for the standard gauge vehicle, these structure types get very good distribution of load across the width of the bridge. So we were looking at, all of these were at the same width. We had a 32-foot wide bridge we were running, and at 32 feet wide, a standard gauge vehicle distributes, there's a significant portion of that load all the way across the bridge. So you just don't gain that much by spreading the load out, is what the results showed. And this was consistent, and then these are not typically modeled this way, but the way we modeled it was consistent with the way the AASHTO distribution factors were calculated, as far as how we linked those beams together. And we did compare the single lane distribution factors to our standard gauge results, and got very good agreement. So we did calibrate our model that way, and this is what the results showed for those the non-standard arrangements and the multi-wheel line arrangements. So upon completion of all that data, we then did an analysis of the data statistically to look at correlation between the various bridge characteristics and vehicle characteristics to the force, the moments and shears of the various different bridge types. And these are expressed in terms of a correlation coefficient, which that varies from -1 to 1. -1 meaning it's perfect negative correlation, it's inversely proportional. The +1 means positive correlation, and 0 means it is not correlated. And what we found with those results is that there is very good negative correlation between gauge width and the number of wheel lines with all of these forces. So the wider the gauge gets, the more wheel lines you get, the lower the correction factor becomes. What we did find was very little correlation between all of the bridge data points and the results. And I think that's mainly due to the complicated relationship between the beam spacing and the various axle gauges. So it's a very complex relationship between all those factors. We did get some weak correlation between the moment results and span length and beam stiffness for the non-composite and composite box beams. But other than that, very little direct relationship for any of those factors. So in compiling the final correction matrix, what we see on the right is the correction factor. This is for all bridge types by vehicle, and we did isolate in our results. So we've got the 34 vehicles here, the characteristics of that vehicle, and then this is the correction factor considering all bridge types. This is the correction factors with the box beams excluded, which we'll talk about in a few minutes, but we did end up separating those two because of the wide difference between the box beams and the other structure types. But what we found here in reviewing those results is that there were a few of the type 2 vehicles, which are the most common non-standard gauge that are encountered for permit applications. A few of those axle configurations were controlling the correction factors for those types of vehicles. And at that point, ODOT conducted a review of the vehicle types we were examining against a wider set of vehicles that they had received permit requests for, and determined that a lot of these were really uncommon as far as what they encounter, and they elected to eliminate a few of those that are uncommon or that they don't see at all from the study before we tabulated into a final correction factor matrix. So those the vehicles that are shaded in red there on the right were eliminated prior to the assembly of the final matrix. And this is the final matrix including all vehicle types. So this is taking the worst case correction factor based on the gauge width and the number of wheel lines. So we've got 2, 4, 6, or 8 or more wheel lines, and then a factor corresponding to the gauge width, which is the gauge width being defined as center to center of the outside wheel lines. We determined that the gauge width often gets reported as the total width of out to out of wheels. So we included both in the table, assuming these are dual wheels, and there's an approximate 1 foot difference between the face of that outside tire and the center of the dual wheel line. So we included both of those columns in the table. And this version of the table is largely controlled by the side-by-side box beams. So for that reason, we created an alternative table that has box beam bridges excluded. And this one gives a much lower set of correction factors. There's not currently a means to apply these factors directly into OHPS right now, but ODOT is working with ProMiles to find a way to incorporate this into the system so they can separate these bridge types from the others as far as the correction factor selection. This is a side-by-side comparison of the two, and you can see that a lot of these, the 16-foot four-wheel line is a very typical structure type or a vehicle type they encounter, and you can see that drops from 0.85 to 0.7 between the two matrices, and a lot of these wider arrangements have a pretty sharp reduction between the two. So that's the reason for separating out the box beams from the all bridges table. In addition to that matrix, also in our report, we provided a correction factor matrix for each vehicle we ran. So you can see here, this is configuration number 12. So this is the type 2 with A and B of 4 feet, and we give in these tables the controlling correction factor for all bridges, the controlling factor if you exclude the box beams, and then for each structure type we ran and for each force we looked at. So non-composite box beams spans of 33, 47, we're giving correction factors for those individual components. So if there is a case where you want to look at a specific structure configuration with a non-standard gauge vehicle, we've got a tabulated correction factors for everything we looked at so that those numbers were available for use. And with that concludes our presentation. So thanks everybody for attending, and we'll be happy to answer any questions. And I believe I see a question from Amjad, Technical Advisory Committee member Amjad has asked, what does the peak at near 16 feet represent? So let me go back to for the concrete slabs. I guess it's in both. What I'm guessing that is, Amjad, is that has to do with the vehicles, the specific vehicles in the set we looked at. So let's go to the arrangements. So the overall gauge width is here. So it's either this 16-foot vehicle or this one. I am guessing it's probably vehicle 27, where we've got a bunch of very closely spaced wheel lines. We've got A, B, and C dimensions of 2.42, 2.0, and 2.33. So everything's very tight. And I'm guessing that's what that represents, is a controlling case for a single arrangement or axle arrangement that we looked at. Okay, any other questions I can address?
We do not have any other questions that have come in at this time.
Okay, well, Paula, should we wrap it up then?
Yes, we just have another comment that just says good research and excellent presentation by both, and thank you for your time. So yes, with that, we will go ahead and wrap things up, and I will send a follow-up email with the copy of the presentation and a copy of the recording to everyone.
Great, thanks a lot, everybody.
Thank you for your time.
Thank you, everybody.